I am going to talk about enhancing recognition of historical musical pieces with synthetic and composed images. This work was developed by myself and Sánchez, my PhD director, and what I'm briefly show is the introduction, then the proposed techniques of synthetic image generation and more specifically image composition, the experimental method that was and how it was developed, and the results on the matter. So, as we all know, a huge amount of historical handwritten musical pieces are not available, and the task of making them available is insurmountable without considering automated technologies. Deep neural networks are the state of the art in the field, and although lately transformers have been obtaining high quality transcripts of many types of musical pieces, as we've seen before in this very conference workshop, we also have to take into account the more classical models in deep neural networks, such as convolutional recurrent networks. And what we propose here is two techniques to improve on the recognition capabilities in data scarce environments for these deep neural networks. These techniques are the use of synthetically generated images and image composition within the historical musical document to approximate the capabilities of recognizing complete pages. So, for this, first we're going to see a synthetic image generation. We generate synthetic images, of which we will see some examples following this slide, and they are based for synthetic text samples. We use 15th century chants, which are very similar in mode to what is expected to find in the data, in the real data. And for musical image generation, the samples from which we generate the images, we utilize a syllable-based language model. There are three different levels of Gaussian noise that were applied to these synthetic images to generate some distortions and be able to approximate in some manner real images, real historical data. And we perform the experiments using a varying number of synthetic images, with baseline experiments that don't use synthetic images at all to experiments with up to 10,000 synthetic images. Now, here we see the comparison between a real image and a synthetic image. This is for the case of lyrics images, and we can see some differences. Even though the TypeScript is the same, we can see that there are decorative elements or the lines of the staffs that can be seen on the historical image but are not found on the synthetical one. And for the musical images, we can see that there are these differences also present here. As we can see on the original image, on top we can see the lyrical line that's under it, but the idea is to find images that are similar in style to the original images. Now, these images also have the different levels of noise, as we said. Here we can see how this noise is introduced in three levels. In the first level, we introduce the Gaussian noise, and we increase the amount of Gaussian noise that we use in each of these levels. We can see it here for lyrical images, and we can also see it here for musical images. In the case of musical images, it's important to note that here we have only shown images with 4 lines in each staff, but there are other than tetragrams, there are also pentagrams with 5 lines in the dataset, but we'll talk a bit more in detail about the data once we reach the dataset part. Now, I went rather briefly over the synthetic image generation part because this is a well-known technique to most of us, but I will go into a bit more detail, at least within the idea of image composition. The idea of image composition is to join all the lines that are found in a single page. This allows the model to learn the content of the whole page, but work at the line level. because we have all the lines in the same sequence of information. This helps bridge a gap between line-level recognition and the context of a complete page, even though it lacks certain elements, such as decorative elements that are not completely captured by the line detection and extraction process, which still needs to be performed. It allows to implement different relationships between the elements at the end of one line and the start of the following one, which are really important, and also long-term relationships that can only be found when the whole content of a manuscript is explored once. The experiments are performed with composed line images, both in the training and decoding processes. And this will also be done with composed synthetic images. For this composition process, here there's an extract of an original image, just the first part of the image, but take into account that the whole image would be used if in the real process. Now, for this image, for the lyrics part, we would detect the lines and extract them. And what we can see on top is 3 lines that have been detected and extracted. And we would compose them by piecing them side by side in the reading order. It's important to note that the reading order in this type of manuscripts, when only considering either musical elements or lyrical elements, this is narrative elements are not considered, is pretty straightforward, as lines are read top to bottom and left to right. And we can see here that the whole line with the content of all 3 separate lyric lines would be present in the single sample that will go to train the model or then decode it. Now let's see how both of these techniques are applied and what characteristics does our dataset have. We have worked with the Salcines dataset, which is a 181-page dataset of images of historical musical documents with 2,251 pairs of staves and lyrics. There are additional narrative texts, as we said, but these are not considered. These are usually read either before or after the musical line that they are present with, but in this work we only focus on staves and lyrics. There are 46 different characters for the lyrical elements. This is upper and lower case characters for most letters of the alphabet, and 20 different symbols, which include notes and keys or clefs for the musical part. And we did 5 splits of cross-validation with a 70% of pages used for training, 10% for validation, and a 20% size test set. For the architecture we use an optical model base of convolutional recurrent neural networks implemented with PyLaya system, a language model, which is a 12-gram model estimated with SR-ILM, and we combine both of these models with the Caldi software. There are varying amounts of synthetic data, as we said, from 0 to 10,000 images. We use the image composition method in training and decoding, and we also use the combination of both techniques, where composed images are used as synthetic images too. Now let's go to the results. Here we only show results for the best case scenario for amount of synthetic samples and Gaussian noise. In all cases, the best results, except one edge case, all best results are found with 7,000 synthetic images, which is about 3 times the size of the original dataset, and a 50% Gaussian noise, which would be the second level of noise we saw earlier. We can see that the best results for the music case are present when composed images are considered, and there's not a notable difference whether synthetic images are present or not. We can see that in both cases, the introduction of synthetic images by themselves improve upon the results, but this improvement is within the confidence intervals, therefore it's not notable. However, there's a special interaction when considering synthetic and composed images for the lyrical elements. This is because the training process, when considering composed images is much more complex, as the model needs to learn a much longer context and a bigger amount of characters for each sample. Therefore, the training process finds a series of slopes and valleys where it gets stuck much earlier than the traditional process or the traditional way one would expect. In the case of lyric images, the moment we introduce synthetic images to the composed image training, we see that in most of these valleys, the model is able to go over them and reach a much greater results. And as we can see, especially with the introduction of composed images, there's a noticeable improvement in the quality of the transcription. This data is also composed of syllabic separation. This is because traditionally this kind of music is separated by syllables, and in this data set we also evaluate the character error rate and the syllable error rate, which is in both cases for every model the best. For composed music images, both THER and SER are the base case scenario, and for lyrics, the synthetic and composed images. Now, as to conclude this work, the idea is that both techniques help improve upon the results, and we can see, based on these results we saw, that composed images are the main contributor to most of the improvements found, which makes sense given that the ideal scenario is when we work with the whole context of a musical piece. The more context we have, the easier it is for the model to learn and precisely determine which decisions it has to take for the transcription. This also shows that we can approach a complete page recognition profile even if we work at the line level, at the line of the transcript itself. It's true that we are losing a lot of context based on the context of the page, but we are able to, regarding the content of the document, study the whole document at the line level. Additionally, these techniques are agnostic to the field, and it's really easy to see how you could apply techniques like this to a different field. That's within the character recognition paradigm. And this is the work that we developed, and if you have any questions about it, I don't know if I went over time or if I got
a little
short,
bit.
but okay, I'm sorry.
Well, I think we have
Any
time
question?
for, yes, at least one quick question. Anybody? Okay. Oh, okay, Antonio, go ahead.
Hi, Manuel.
Right.
Congratulations for the work. I was just wondering if you could elaborate a little bit more on how do you produce the synthetic data, and how do you manage to print all the symbols and also the lyrics of the images?
Okay, for the lyrical part, we obtain chants that are public chants from the 15th century, as this data set is from the 15th century, and we use a Latin software to separate them in syllables, as the data is found in syllables. That's for the lyrical part, and we use those texts to randomly generate with the, I don't remember the name of the software exactly, but it's on the paper itself. You can find the software we use to generate the images. For the case of the musical images, we developed the software to generate the staves at the notes at the different lines. And for the text part, which is the more complex part, given that we need a syllabic transcription that's not necessarily already present in the ground truth, because in that case it would overfit. What we did is train a language model based on the syllables. And we generate, using that language model, sequences of musical syllables that should have a very similar distribution to the ground truth distribution without being replicated samples from it.
Okay, thank you.
Welcome.
I said one, but Bertrand, go ahead. No, go, go. This is
okay. It was very quick. It was just to know if you tried or you intend to make some distortion, geometric distortion on your synthetic data. And on the slide 6, it seems that there is some artifacts on the images you generate, but maybe it's just the way you copy and paste the image. Not the previous one. Yeah, this one. You have vertical artifacts. I don't know if it's
On the top image, you're referring to the top image
no,
here?
on the bottom image. You have vertical shadow.
Yes, that's because for okay. So on one side, regarding the distortions, we want to explore more types of distortions for our synthetic data to generate better synthetic data and approach as with as much fidelity as possible real images. But as for this work, we try to limit the amount of distortions we applied, not to create an exponential number of experiments we needed to perform. But it's something we are working on. And in the case of these artifacts, it's because the way we created the synthetic data, the images themselves, the software we have has different kinds of shadows and similar modifications to the background of the image. These are according to the background you can see on real data.
Okay. Okay, thank you.
Seems like replicated JPEG compression artifacts, but
Yeah, it could be, yeah.
okay. Well, Manuel, thank you very much for your talk.